We started with the concept of limits, and we developed limits. We developed the concept of the derivative of a function f, that is the limit of the difference quotient. In calculus 1 is called differential calculus, so a lot about this course is going to be about differentiation. This lecture is going to be sort of eclectic, and it is not supposed to be instead of the lectures on Khan Academy and on MIT OpenCourseWare, but in addition to, sort of, this should be guiding your studying. So it's going to be a little bit eclectic. All right, so let's get started with the fact that, in general, given a function f, f prime expresses the instantaneous rate of change of the function. Basically, at that point, how fast is the function value changing? Specifically, the way we have looked at it, and that was also the birthplace of calculus, is that if you take an object that's moving along a vertical line and define a location function, then the first derivative of that is the velocity function, how fast is the location changing. And if you take the derivative of the velocity function, what you get is the acceleration function. The acceleration expresses how fast the velocity of an object is changing. You will often see just a for acceleration because in a lot of the situations the acceleration is constant. For example, the acceleration caused by the gravitational force of the Earth is constant, but it is simply the second derivative of the location function. So this trinity will show up a lot. A location function, you differentiate it, you get the velocity function, you differentiate that again, and you get the acceleration function. Okay. Throughout the entire course, two ideas will always help you to have an intuition about the derivative, and those are the following. These are going to be very important things to remember. Number one, the derivative measures the slope of the tangent line, and number two, even if it's specifically stated otherwise, we can always think of f and f prime as location and velocity functions. So these two ideas will be recurring and will motivate a lot of ideas. So remember them. Okay, so a few definitions. These concepts are going to join our growing list of complete analysis of a function. A function f is strictly increasing if for all x1 and x2 in the domain, if x1 is less than x2, then f of x is less than f of x2. Geometrically, that means that in a strictly increasing functions graph, between 2 points, the one on the right is higher. So x1 is smaller than x2, then the same relationship should be true for the function values. F is not strictly, just f is increasing if for all x1 and x2 in the domain, if x1 is less than x2, then f of x1 is less than or equal to f of x2. The only difference between the two definitions is that less than or equal to is allowed, which makes for interesting things. For example, a constant line is increasing. We're not going to go over it, but we can very similarly define strictly decreasing and decreasing. And to make matters worse, you know there are two notations like Leibniz notation and Newton notation. Well, there are two labels floating around and they're all over the place, both of them. So sometimes you will see strictly increasing and increasing, but sometimes, and this is confusing actually, sometimes you're going to see increasing here and non-decreasing here. So I will usually use strictly increasing and increasing, but you might be using books or other resources that use increasing and non-decreasing, and this is always a fair question. If someone says increasing, then that's confusing because it could be either strictly increasing or non-decreasing. So that's always a fair question. Okay. In our complete analysis, we're not just going to say yes or no. We're going to be a little bit more specific. For example, if f of x is x squared, then we're going to state the intervals upon which the function is decreasing and increasing. So in the case of the complete analysis of f of x equals x squared, we're going to say that it is decreasing on minus infinity 0 and increasing on 0 infinity. These statements would be true if these were half closed intervals, but we're going to use the convention that just for sake of simplicity on MyOpenMath, just use open intervals. You see, increasing, decreasing behavior is defined over an interval or in the domain, which usually the domains that we're going to see are intervals. And so the definition will work for open intervals, and for closed intervals, we're going to use in homeworks, exercises, we're going to use open intervals for that. But this is how we're going to discuss increasing, decreasing behavior. Okay. Differential calculus has two obsessions. One of them is tangent lines, the other one is maximums, minimums. Maximum is singular, the plural is either maximums or maxima, same thing, minimum, minima. And when you just want to say a maximum or a minimum, we use the expression extremum, or the plural is extrema. And so let's say we're looking for maximums. So there are two types of maximums that we can have, the one that we want and the one that we can easily have. And unfortunately, those are not the same. We're not going to define both maximums and minimums. Minimums are analogously defined, and you can find those in the handout. So f has an absolute maximum xm, f of xm, if for all x in the domain, f of xm is greater than or equal to f of x. Equality is allowed. So if you think about the sine graph, because equality is allowed, every single top of these waves is an absolute maximum. Basically, you can just simply think of the absolute maximum as the highest point on the graph. Well, highest in the sense that there is no higher. You can have tie. These are the ones we're looking for. We want to maximize profits, minimize risk, minimize pollution, and so on. So these are very reasonable things that we're looking for. However, what we're going to easily find are not absolute maximums, minimums, but relative maximums, minimums. Now, a relative maximum is at a point that cannot be the end point of the domain. So it's an interior point of the domain. That's very important. And second, we can restrict f to a smaller domain so that on that smaller domain, it is an absolute maximum. So let me show you examples. So this here is a relative minimum. Why? It's not the endpoint of the domain, and we can restrict the function to a smaller domain so that on that restricted domain, this point becomes an absolute minimum, right? If we just look at this part of the function, this point is an absolute minimum. So it's a relative minimum, but it's not an absolute minimum because this point beats it, right? So relative does not imply absolute. Now, for an absolute maximum, this is the highest point on the graph. So this is an absolute maximum, but not a relative maximum, because for a relative maximum, you have to be inside the domain. This is an endpoint of the domain, so that's not allowed. So absolute does not imply relative either. So it's not as straightforward as a connection as we would hope for, but they can coincide. For example, this is both. This here, both a relative minimum and an absolute minimum. So what's going to be the experience is that we are looking for absolute maximums, minimums, but what we can easily find are the relative ones. To make matters worse, there are, again, two types of expressions used. And again, they're all over the place. Sometimes I'm going to use the relative and absolute, but just as often you're going to see local and global. Those are absolutely the same things. They're just there to confuse us. Nowadays, most videos, they just mention both to get it out of the way. Okay, so that's about maximums, minimums. So I might have already mentioned that until December, when this course is over, you're not allowed to forget these two ideas. And those are that the derivative measures the slope of the tangent line, and that a function and its derivative can always be thought of as location and velocity functions of the same object. Now let's see what those things mean. Here is an example. F of x is x squared. The derivative of the function is 2x. That means that any point you would pick, there are 3 points as examples. If we pick x equals -2, then the function value is 4, right? And if we were to draw a tangent line to the graph at that point, so the point of tangency is at x equals -2, then the slope of that line would be whatever is the derivative at x equals -2. So if we put -2 into the derivative, we get -4. That is the slope of the tangent line. If we take x equals 0, then the function value, the point is 0, 0. If we put 0 into the derivative, we get 0, which is indeed the slope of the tangent line. And finally, here is another example. If x is 3, then the point on the graph is 3, 9. And if we were to draw a tangent line to the graph of this function at this point, then the slope of this tangent line would be whatever the derivative says it is. So we take the derivative and we substitute x equals 3 into that. That is what the slope is of the tangent line at that point. So in this case, f prime of 3 is the slope, which is 6. Now let's pick another value, say x equals 10. If we are asked to write the equation of the tangent line that is drawn to this graph at x equals 10, what do we need for a line? We need a point and a slope. At x equals 10, the point of tangency should be 10, 100, and the derivative should be measuring the slope of the tangent line. The derivative of the function is 2x, x is 10, so this slope is 20. Basically, the slope of this tangent line is the value that the derivative takes at 10. We have the slope, we have the point, so the equation of the tangent line is going to be 20, that's the slope, times x minus 10 equals y minus 100. And then you know how to take that further and simplify it to get the slope intercept form. You're going to see a lot of problems about tangent lines. Tangent lines is one of the two obsessions of differential calculus. And there are going to be lots of applications with tangent lines. And whenever you see these intimidating word problems about tangent lines, remember the following. Given f and a fixed point, and we draw the tangent line drawn to the function at that point. The tangent line is a line, right? That's a linear function. So what we have is two functions that agree with each other at two levels. They have the same function value, right? F of c and g of c are the same value, and they have the same derivative. That is the same as having two objects' motions where at that point they have the same location and the same velocity. Not forever, just locally, right there. And so the tangent line is the simplest function that does that does have the same function value and the same derivative at that point. And so oftentimes you're going to have two unknowns, and these are going to give you the two equations. So keep that in mind. These two ideas, I keep bringing them up, that the derivative measures the slope of the tangent line, and that we can always think of f and f prime as location and velocity functions. These two ideas will give you motivations for fundamental connections between a function and its derivative. For example, if f prime is positive, then f is increasing. Now that sounds a little strange at first, but let's just think about it in terms of location and velocity. F prime is positive. Let's think of f and f prime as location and velocity. So that means that f is location and f prime is velocity. So f prime is positive is the same as the velocity is positive. Now what does that mean, the velocity being positive? That means that the object is moving upward, right? And what does a location function look like if the object is moving upward? It's increasing. And so here we are, if the derivative is positive, then the function is increasing. What about the tangent lines? F prime is positive. That means that we can draw, this is the tangent line drawn to the graph. It's very difficult to draw a decreasing function when the slope of the tangent line is positive. So if the slope of the tangent line is positive, then the line itself has a positive slope. The line itself is increasing, and it's easy to feel that that means that the function itself has to increase. So if the slope of the tangent line is positive, that's the derivative. So the derivative is the slope of the tangent line. If that is positive, we have an increasing line, increasing tangent line. That can only be the tangent line to a function that is increasing there. Okay, let's see another important connection. And this one is interesting. So if the derivative is 0, then f is constant. As it turns out, you will see in 2 minutes this is going to feel very natural. But even though it feels natural and fundamental, we're going to have to develop a lot of theory to actually rigorously prove this fact, even though it's so intuitive. So let's think location and velocity. If the velocity is 0, how can we describe the motion of the object? It's sitting at a point. Well, then the location function is constant. Done. Let's go back to this. This one is really important, that if the derivative is positive, then f is increasing. Analogously, if the derivative is negative, then f is decreasing. We're going to use this fundamental relationship between a function f and its derivative f prime to find local maximums and minimums. Suppose a function f has a local maximum at x equals c. A local maximum is characterized by the function is increasing before the number c and decreasing after. So f is increasing before and decreasing after. Well, but that's the same as f prime being positive, right? The tangent line slope is positive, or the object is moving upward, so the velocity is positive. And after c, f prime is negative. Same thing, the slope of the tangent lines is negative, or if the location function is decreasing, the object is moving downward, therefore the velocity is negative. So they both work. So this is what we're going to look for. We're going to look for numbers c such that the derivative changes sign from positive to negative for a maximum, and for a minimum, it's going to be the other way around, right? So before the number c, in case of a local minimum, we have a decreasing behavior on the function, and after c, we have increasing. That means for the derivative that it must change sign from negative to positive. So basically, a function has a maximum or a minimum if the function itself is continuous at c and the derivative changes sign from positive to negative for a maximum, and from negative to positive in case of a minimum. How do we find these points? First of all, you can have minimums where the derivative doesn't even exist. Consider f of x equals absolute value of x. Now we know that when we take the difference quotients limit, the left limit is -1, the right limit is +1, therefore the derivative, a two-sided limit, does not exist at 0. So f prime of 0 is undefined. This is a relative minimum. When we're looking for maximums, minimums, we need to consider that maybe the derivative doesn't even exist there. But here is the good news. If the derivative exists, it must be 0. And sort of what goes wrong here reveals why. Well, the derivative was -1 on the left of 0 and +1 at the right of 0. And that's no accident. Let's look at the minimum. So this here is c. Now, the derivative exists, right? So suppose that f prime of c exists. But if it exists, it's a two-sided limit of the difference quotients, right? And if you look at the difference quotients to the left of c, these line segments have negative slopes. So all the difference quotients are negative. And after c, all the difference quotients, the slope of these secant lines, are all positive. And yet a two-sided limit exists. There is just one number that can be approached through positive and negative numbers, and that's 0, right? If you're really, really close to a positive number, you are positive. If you're really, really close to a negative number, you are negative. The only way you can have a two-sided limit where the left limiting values are negative and the right values are positive is that the two-sided limit, if exists, it must be 0. What this tells us is that if f has a local maximum or minimum at a point c where the derivative exists, it must be 0 there. So when we're hunting for maximums, minimums, we're going to look for two types of numbers where the derivative either doesn't exist or 0. And those are called critical numbers. So remember, we're looking for change in sign in the derivative, but now we concluded that only happens where the derivative is either undefined or 0. So would the local maximums, minimums be at the critical numbers? So maximums and minimums are only at critical numbers, but that may not be enough. All those critical numbers that we found may not necessarily be maximums or minimums. Here is an example. Consider f of x equals x cubed. The derivative of the function is 3x squared. That takes a 0 at x equals 0, and it looks like the function locally is horizontal, the tangent line has a slope 0, so it does work. But the derivative 3x squared is positive before the 0 and positive after the 0, which is the same as to say it's increasing before, increasing after. That's not a maximum or a minimum, right? So the first derivative test is first find all the critical numbers and then look for change in sign in the derivative. If you don't have a change in the sign of the derivative, you do not have a maximum or minimum. But if there is a change in sign in the derivative from positive to negative, that means that there is a change in behavior of f from increasing to decreasing. That is a maximum. Decreasing, that is a maximum. And you can just play it out with your hand. You do not have to memorize it. If the derivative changes sign from negative to positive, then f, the function itself, will change behavior from decreasing to increasing. Now that's a relative minimum. And so that is what we call the first derivative test. Look for critical numbers and look for changing sign around them. Thank you for watching.